For today, however, I would like to talk to you about what diagenesis is, or at least confirm what we've talked about previously. Then we're going to focus in on cementation and alteration and mineral replacement. Diagenesis, as you will see in a second, refers to all changes that take place to sediment after its initial deposition. Everything. That includes cementation, but it also includes the changes that take place within the grains themselves, mineral alteration, etc. Okay? Alright, so let's get started. Diagenesis is defined as all changes to sediment or sedimentary rock from the time of deposition to the onset of metamorphism. Folks, if rocks do not get metamorphosed, this means diagenesis can cover the entire history of the planet. And indeed, I have looked at Proterozoic and older sedimentary rocks that were never metamorphosed. And what you're looking at is a record of billions of years of time. Changes that occurred to this rock numerous times. Now, this little chart here shows you how this works. Deposition is that time when sediment is rolling around, being added, being deposited, being thickening over time. From that point on, every change that happens to that sediment is part of diagenesis, up to a stopping point. And that stopping point is the onset of metamorphism. Now, you've all had David Allison before for petrology, and you're all aware that metamorphism covers, again, an incredible amount of factors, variables, and regimes. Low-grade metamorphism and later stage diagenesis are virtually impossible to distinguish because basically they're the same thing. But once you start getting the high-grade metamorphism, once you start taking a sedimentary rock and changing the orientation of particles because of pressure, or modifying them because the pressure and temperature are increasing to the point where the minerals themselves are no longer stable, that starts becoming more of a metamorphism concern. Okay? So most sedimentologists at this point don't look at these rocks anymore. In fact, we don't even acknowledge their existence. From this point on, they don't exist as interesting rocks. They become basement. If you're a David Allison type person, this is when things start to get interesting. And he would say that, no, that's not how it works. These are the fun rocks. Everything below this point is pre-rock. We've had this discussion numerous times, usually in bars in places like Denver after a conference is over. And it's funny because you'll see everybody around the bar nodding when I'm saying something, and then when David says something, the other half of the bar will be nodding because this is this is the difference between hard rock and soft rock geologists right there in that diagram. Now, what are those changes? And here's where things get really exciting, because every change can include a simple matter of taking the sediment and churning it around. So technically, burrowing is a form of diagenesis. It's called biodiagenesis if you want to subdivide it up into something finer than that. And if you think about it, if you have sediment sitting there in the subsurface in the marine environment, minding its own business, and then something comes along and goes through it, disturbs it, churns the sediment, brings it up to the surface, what you've done is you've changed the chemical regime. The waters that were down below were probably reducing because there's a lot of organic material in it. If you bring it up to the surface of the sea where there's more oxygen, you have changed the conditions. That ultimately can give rise to changes in the chemical regime, which will lead to perhaps differences in cementation or even dissolution. Okay? So burrowing, boring, incrustation, anything that is biologically driven is a form of biodiagenesis. Now really, when it gets to the exciting stuff, the stuff that I'm more interested in, I'm more interested in what happens to the sediment after it's taken out of a marine environment and put into other diagenetic environments where the water chemistry is going to ultimately change. All right? Under these conditions, when you start burying sediment, the sediment will start to get compacted. You will change the amount of porosity and permeability. Cements are going to start to come in. As the water chemistry changes, you're going to start changing what is stable. Minerals like aragonite are unstable once you take them out of a marine environment. And if they're unstable, they're going to change to something else. Dissolution of grains is common. If you squeeze them too much, you start getting something called pressure solution, which again is something David Allison would have talked to you about. But it happens under diagenetic conditions too. Two quartz grains being compacted together. You bury a sandstone down maybe a mile down, which is nothing. What can happen is those grains will now start to feel pressure that's focused at their points. You can start to induce dissolution of quartz along the points where those grains come in contact with one another. Where does the dissolved silica go? It migrates and can form cement somewhere else. These are all the potential changes that can occur that are driven by burial and chemical changes. Replacement, recrystallization, fracturing, you name it, all these things can and will occur to sediments. Now here's the neat thing about diagenesis. If you have good rocks and a keen eye, not only can you identify what the last events were that happened to a rock, but you can identify what all of the events were that affected a sedimentary rock. In other words, the complete alteration history that in some cases can go back billions of years. And consider what this means. Since a lot of these changes are going to be driven by changes in pore water chemistry, that means you can get an idea of how the water has evolved over time. This is paleohydrology. All right? In other words, to be able to determine the chemical variations that have taken place. And I've used stuff like this to more or less show how areas have been influenced by things like sea level change, because you can actually see how the water chemistry might become more marine over time or less marine over time. A very common thing that you can do if you've got good rocks. Now, incidentally, one of the other questions that I asked you on the midterm was, if you had a chance to study sedimentology anywhere in the world, where would it be and why? Well, again, what I was looking for was not a travel log. I mean, simply saying you want to go to New Zealand because you heard it was cool and they have good wine and a good rugby team. That's not what I was looking for. What I was looking for is I want to go to New Zealand because there are places in New Zealand where you can actually see how pore water chemistry has evolved over the last 50 million years and get a really good record of climatic change. And of course, that requires a little bit of thinking and understanding of things. And that ultimately is what I was looking for in questions like that. But it's driven by observations like this. Let's talk about cementation again. Nothing new here. We've talked about cements before. Cements are pore-filling minerals that are precipitated into void spaces after deposition. In the past, we've ignored the cements. I mean, you couldn't ignore the fact that they were in your sandstones, but I told you to ignore them because we weren't going to deal with it now. Now is now. A reminder, cement and matrix, the two things are very similar in terms of where their positioning is. But matrix is the stuff that is brought in and deposited at the same time as the grains that make up the sandstone are deposited. Cement is a chemical precipitate that comes in afterwards. And again, I said long after deposition, but as it turns out, you can get cements that form on the sea floor. Multiple phases of seafloor cements are possible under numerous situations. So that long after deposition is not necessarily long after. But I do want you to realize that as long as pore space exists in a sedimentary rock, it is capable of being filled in by cements. You can have a 2 billion year history of cement within some rocks if the conditions were favorable for that stuff. What kind of cements can you get? Boy, folks, this is a mineralogy class now, because water, which is the ultimate source of all of these cements, can dissolve and hold an incredible variety of minerals. Cements, and these are common cements, include quartz, the standard type of alpha quartz that you would get by buying a quartz crystal. Chert, chalcedony, opal. These are all the tectosilicate quartz-rich minerals that we stuck you with in the last days of mineralogy crystallography. You can also get the iron oxide cements. You can get hematite, limonite, or combinations of these. I have never seen a magnetite cement, but that doesn't necessarily mean something like that might not occur under some situations. There are different phosphates that can form, different clay cements, and of course the ever popular glauconite. You can get the carbonate minerals, calcite, aragonite, high magnesium calcite, dolomite, siderite, anchorite. You can get them all. And by the way, we haven't had a chance to talk about magnesium calcite at any point, at least I don't think. Has Dr. Clark ever talked to you about magnesium calcite in paleontology? Ring a bell at all? high magnesium calcite, low magnesium calcite? All right. We'll talk more about that in terms of the diagenesis when we get to the carbonates. These are minerals that we generally focus in on the latter part of this course with carbonate diagenesis, which is my personal favorite type of diagenesis. There are many more cements that can occur here. And in fact, I'm continually surprised by the types of cements that people will find in sedimentary rocks. Now remember, if a mineral is capable of being dissolved in water, it can be precipitated out from water. Also remember that diagenesis, as defined, goes right down to the onset of metamorphism, which means you can have water temperatures that exceed 500 degrees Celsius. If it's buried deep enough, the water that hot will dissolve out just about every mineral you can think of, including gold. But as I said previously, some minerals don't seem to form as a precipitate in these conditions. I have never seen a gold cement in a sedimentary environment. Although that would be a cool thing to find, man. Real cool. What do these cements look like? Well, actually, again, just a reminder of what the characteristics are for cement, okay? Remember, I gave you these things a while ago, distinguishing between matrix and cement. Now you have to start looking at the cements. They tend to be homogeneous, chemically pure. They line pores, meaning that they tend to fill in the void spaces. They have specific fabrics, which I'm going to show you more of these in just a few minutes. Multi-phased and zoned. I thought I'd show you some pictures of what these cements look like. This is a scanning electron microscope image. I think I've showed... I'm not sure, have I showed many SEM shots in this class? I know I show some of them in mineralogy, but I can't remember if I've showed you any of these before. What you're looking at here now is just what a scanning electron microscope would show you of a sandstone. Very clearly you can see the nicely well-rounded grains here. What you're looking at is a bunch of fine particles that basically are filling in the void space. Now under this type of observation technique, everything has a bit of a crumbly look to it, but this is a fairly well-developed cement that you're looking at here. This is probably a clay cement of some sort. But notice it fills in the void spaces and coats the grains. All right? The quartz grains themselves are relatively well-rounded and rather spherical here as well. Okay? Here's a shot I've showed you previously, and again, this is not the world's best shot because sometimes cements that are not optically clear are not easy to see. But what you're looking at here is a sandstone with at least 3 phases of cements that are identified. There's a quartz grain in plain polarized light. You can see the dark stuff that clearly is filling the void spaces. There's actually 2 colors here. There's a little bit of green, that's glauconite, and this stuff has a brownish color to it. That's hematite. But even before that, there is a thin layer of quartz cement. 3 phases of cements. This is what we're talking about, multi-phased pore filling. So basically what you've got is a situation where you've got void space. The first cement comes in, and in this case the first cement is actually a quartz cement. In some cases it can fill up the entire void space. Once it's filled up, no more cement can fill in there. But usually what will happen is you'll have a little bit of void space left behind, and then later on another phase of cement comes in. That's what you want to look for when you're looking for diagenetic phases. Find the grain boundary. That's where the deposition stops right there, and everything from here inwards in both directions becomes the diagenetic phases. It's phased. First phase is quartz, second phase is this dark stuff you see here. Okay? Here's another SEM shot. You notice I intentionally drew the cements around the quartz grains as being hexagonal. That's what it looks like. A quartz cement is a chemical precipitate. It is quartz. If you grow quartz from water, quartz will grow crystal faces. That's why you see these beautiful hexagonal crystals when you go to buy quartz in a mineral shop somewhere. That was just a big quartz crystal that grew in a big hole. You're dealing now with small holes. The quartz grows into small crystals. But if you have the means by which to resolve them, like a scanning electron microscope, you can still see that they're following the rules of crystallography. It has to. It's a chemical precipitate. That's a small ROM that, in this case, is 0.5 millimeter across from that point to that point. really tiny. And when you look at it under a microscope, and again remember, under a microscope you have the power to see things 400 times or higher magnification if you want it. Under those magnifications you can start to see what will be clearly euhedral crystal boundaries because of the chemical precipitate. Quartz overgrowth cements, as you see here, are really characteristic when you see them in thin section. And at least some of the thin sections I gave you in the first thin section lab, the ones from Dolphin Island, basically are quartz overgrowth cements. I asked everybody to look at those. When you go back and look at those cement thin sections for your for this lab that you're doing this week, look to see if you can see the euhedral faces. Moreover, and this is really cool, the nice thing about quartz overgrowth cements, because they're chemical precipitates on top of a quartz grain, they tend to carry on the optical characteristics of the grain. Case in point, if that's the optic axis of a quartz grain here, that's the optic axis of a quartz grain there. When the cements start to form over top of those grains, like so, the cement that forms is in optical continuity with the grain that is precipitating on. All right, folks, see if you're paying attention. If the cement and the grain are in optical continuity, what does that mean as you rotate the stage under cross polars? They both go extinct at the same point because they are essentially the same crystal. That's cool, isn't it, if you think about it? Now, one thing to note, a lot of times when you look at a thin section of a quartz arenite sandstone, what you'll notice is really sharp angular grain contacts. This is very common. Many people would look at this and say it's a, quote, angular quartz grains. It's actually not angular. If you look closely, what you'll see is within each of these angular components is a rounded quartz grain. But the only way you're going to be able to see the edge of the grain boundary is if there's something unique along the base of that grain. Now going back here just for a second, notice how all these rounded grains are kind of pitted? They're not smooth, they don't look like they've been water washed. That probably is because there's a little bit of pitting. In some cases, if you have sand grains that are blowing along the beach, every time they impact one another, they get little chips on the edge. It's too fine to see under a normal microscope. But under an electron microscope, you can see that this is not a consistent surface. That gives rise to a very thin dust line. And in some cases, the only way you'll be able to see the edge of the grain is if you see just a little bit of that dust appear in it. Look for that too, because when you see it, it's one of those eureka type moments. The first time you see it and you realize what you're looking at, it is a cool thing to understand. All right? Now, I mentioned to you that cements come in a whole bunch of different fabrics, and indeed they do. Now, here's where things start to get a little bit tricky in terms of identifying different types of cements and different types of fabrics. Remember again, cements are chemical precipitates. That means they are driven by crystallographic rules. That means they must grow like crystals. Depending upon what cement is forming, you're going to get different types of crystals being produced. Sometimes they give rise to very obvious fabrics. Sometimes they do not, depending upon what the mineral actually looks like. Consider the following. Suppose now you've got a sandstone which has a first phase opal cement. Now, opal is not the opal that you're thinking about from Australia where you can buy a pendant and everyone's going to think it's cool around your neck and stuff like that. This is better called opal CT, which is cryptocrystalline, often biogenically produced, non-crystalline silica with a little bit of water in it. When opal forms a cement, In a marine environment, the first thing it does is coat all the grains. Now remember, this is a situation where you have water completely enclosing the grains. You end up getting a very thin precipitating layer of opal. Unfortunately, opal doesn't form really good crystals. So you're not going to see really beautiful crystals of this stuff at all. It's just going to look like a thin rind of stuff around the grain. If that was all that occurred, if opal was the only cement that filled in this entire rock, what would happen is you'd end up getting a very, very fine looking dusting in the interior of the void space. How could you tell it was opal, by the way? I mean, you can look at the fabric. If you knew what the fabric of opal is, you could identify it that way. But what's the characteristic of opal that would allow you to identify it was opal? Thinking petrography again.
So, when you cross the nickels, it's not going to have crystals.
It's non-crystalline, therefore it is isotropic, therefore it goes black and stays black under polars. It will never look like a hole, though, because again it's a form-filling material. So it is isotropic in nature. But let's make this a little bit more interesting. Let's make a change. Remember, I told you that cements can be multi-phased, and this is commonly what happens with the quartz-like cements. How about the next phase of cement being chalcedony? And by the way, this is the type of cements that you get in a geode. If you've ever seen a geode, you'll know you end up getting that very layered stuff with sometimes crystals in the middle of it, like so. All right? Sometimes there's opal in that as well. Chalcedony is, again, non-crystalline. But it's non-crystalline in a very unique fabric. It tends to give you this very fibrous-looking structure to it. It's the coolest thing you'd ever imagine. Now, the fibers tend to radiate perpendicular to whatever surface it's growing on. And by the way, I said fibrous. It's actually a radiating fibrous. It's fan-like structures. All right, so you have this as a second phase cement, sometimes filling it in entirely, like so. But what you'll see is that there is a relationship where there is a perpendicular orientation of those fibers to the surface. That's how you know it's growing from the grain boundary inwards. And of course, sometimes you have to worry about stuff coming the other side and through here where it'll be coming up this direction. But you might even have a third phase of cement where you actually, this last void space here, might have more typical quartz grains. And quartz will be crystalline, multi-phased components. Now, the fabrics you get, and the cement fabrics are, the fabrics in terms of what they look like here, are unique to the cement that you're dealing with. Quartz generally tends to give you blocky crystals that look like this. Chalcedony tends to give you these fan-shaped crystals. Calcite can give you any manner of different types of fabrics. And again, you need to think back to mineralogy. Think of how many different types of calcite fabrics you saw. Calcite forms those nice rhombohedral crystals. And if you see that type of fabric in thin section, incidentally, it tends to be kind of crystals that look like this because the crystals are growing randomly to one another. That's the rhombohedral shaped component. Calcite also forms scalenohedral crystals, dog-tooth crystals. They tend to be a little bit more bladed. Those crystals look like this. The fabrics are dependent upon the cement, but also other circumstances. So sometimes you don't always see the same type of thing. The point I'm trying to make here is that depending upon the cement you're looking at, you're going to see any number of different fabrics. Sometimes they're blatantly obvious. No one's going to confuse this for anything but a cement. But sometimes they tend to be not very obvious at all. Clay cements, for example. If the last phase of cement you had in this little cartoon was clay, what clay is very fine-grained particles, often randomly oriented. What it would look like, for all intents and purposes, is a very fine-grained mud. And of course, that's one of the characteristics that we use for defining matrix. So be careful, okay, when you're looking at these things. All right, let's look at some cements now, just to give you some idea what the pictures look like. I've been pushing the idea of quartz overgrowth cements, and here's a very nice illustration to show you what to look for. Plain polarized light. Here is the original grain edge. This is not a dust coating so much as it is a little bit of hematite stain that is in here. This is all cement. There's the original grain with the original edge, and notice how the extinction of the quartz is identical in both the cement and in the grain. That's what I'm talking about in terms of optical continuity. Here's another grain. Actually, this one's hard to actually see the grain. Here you can see the edge of the grain quite nicely. It's a different orientation. There's the cement, there's the grain, but notice even though it's a different orientation, optical continuity, optical continuity, optical continuity. That is characteristic of coarse overgrowth cements. Some of you saw this very thin section in your first thin section lab in this course. This is the glauconite cement. This is a weird one because this particular rock has both glauconite as a grain and glauconite as a cement. And I have a funny feeling what you're looking at here is a combination of cementation and mineral replacement. Okay, so this one, there are areas here, for example, that looks like a grain that's been replaced by glauconite surrounded by glauconite cement. So I think there's too much glauconite in here to be cement alone. Perhaps when you look at this thin section again, you'll be able to clarify that. Love this thin section. Gorgeous. What you're looking at, it's actually kind of rare to see it this well. Beautiful coarse arenite sandstone. What you're looking at here is hematite. You know it's hematite because it's got a reddish brown coloration to it. Hematite is normally normally opaque unless it's really, really, really thin. And you can get it to show through if you make your thin sections really, really thin. So this is essentially an ultra-thin section, but you can see very clearly how the hematite has come in and filled in the void space, also filled in some of the void space and some of the grains that happen to be there, okay? Under cross polars, because it's thin enough, you can actually start to see a little bit of the birefringence of hematite, which is fairly on the low side, but is nonetheless obvious if it's a thin section. By the way, the terminology that we use in petrography is kind of bizarre. Every time I write something on this, I have to turn off the grammar checker because it doesn't like the idea that you talk about thick, thin sections and thin sections. It keeps giving you errors and stuff, but that's the proper terminology that's used. I drew this very thin section for you because many of you saw this one as well. This is from the Tallahassee Formation, and this is, again, classic. You don't get any better than this. Here is a coarse arenite sandstone. The brownish-looking thick rind you see around here is the opal CT cement, and you can see that it's opal here where you actually have a grain that's not quite an extinct. See that black ridge or interval all the way around it? That's because this is an isotropic material, and then everything that's filled in and through here is actually chalcedony. Not perhaps the best photograph to use, but I hope you can actually see that there's a fanning fiber structure to it. Those of you that looked at the Tallahassee limestone or Tallahassee sandstone before will be able to look at this and actually see some incredibly good areas where this type of fibrous structure actually does occur. And there's a close-up of it. And again, see, coming from this side, what you're looking at here is actually cement precipitating from the underside coming up or coming down from it. So again, beautiful example of a absolutely chemically pure, pore-filling cement that you're looking at. Two phases, as a matter of fact. All right, now let's talk a little bit about the origins. I've alluded to this a couple times, but I want to make sure everyone is clear about how this all works. All sediments are deposited in some sort of sedimentary environment. You have sediment with void space between the particles, for the most part. If you have a very muddy sediment, there's a lot of porosity between the spaces of mud particles, so there's porosity in all sedimentary rocks. Over time, the chemistry of that water will change. All right? So once again, we've looked at this as a standard introduction to petrography of grains before. Now let's look at it from the point of view of how diagenesis works. You have sediment initially deposited in a depositional environment, but then things will change. Then you start dealing with more of what Connors would be dealing with in terms of hydrology. Now he's focusing in on the water. I'm focusing in on the chemistry behind the water. Most cements are going to originate from the pore waters that are in the grains, and as the pore waters change, so too will the cements that are forming in those void spaces. You have to be aware of the differences between the different components of, say, the water table. The vadose zone is the interval of the subsurface that is above the water table. Within this zone, you have grains that have, as within their pores, a combination of water and gases. All right, so let me illustrate what this means to you, or should mean to you. In the vadose zone, water that's present will be trapped between the grains in places like this, along the meniscus. Sometimes you get water droplets hanging on the bottom of grains as well. But note, it's a combination of pore water and open void space. Now the thing you've got to remember is that gases of this are going to be dependent upon what the environment is actually like. It can be oxygenated, it can be reducing, it can be pretty foul. I mean, if you're in an interval where you have a lot of organic degradation taking place, that could be hydrogen sulfide as a gas. The thing to note, however, is that this is going to be a combination of void space and of water. If you drop below the phreatic zone, if you drop into the below where the water table is, now all the void space gets entirely filled in with pore fluids. Now under these situations, again, the water and whatever dissolved gases are in there now can be various combinations. It can be reducing, it can be oxidizing, and it can fluctuate back and forth. When we get to the carbonate diagenesis, I don't know, I'm not sure if you'll be amazed by it, but I mean, this is what really turned me on to the whole idea of doing sedimentology rather than some other aspect of geology, was seeing how many changes can take place and how they can be recorded under a micro. I mean, it still fascinates me we can actually do this. So anyway, in terms of how you get cements, you need to have pore water, and chemicals are going to precipitate from the pore water. The timing of when these cements can form varies from syn-sedimentary processes, meaning at the same time there's depositions taking place, these are the seafloor cements, to burial, right onto the onset of metamorphism. As long as you have void space still in the rocks, you can continue to precipitate cements out. And by the way, it does get even more complex than that, because cements have been known to dissolve to open up new void space for future cements to be precipitated into. The neat thing about this is that the cements themselves give clues as to the origin and the changes of the pore fluids. It can tell you about what the pH was like, what the EH, that's the oxidizing potential of things, what the geochemical variations are. You can trace out pathways of pore fluids by understanding the cements as well. And as I said, you can also get cements precipitating directly on the sea floor. Those of you that are interested in going to some nice tropical places like Jamaica or Belize, Australia, when you go out to the carbonate platforms that are currently forming today, you're not going to find just loose sediment everywhere. A lot of it is stuck down to the ground because the water is so saturated in things like calcium carbonate that you can actually get cementation taking place on the sea floor, okay? And it can be both deep and shallow in terms of precipitation. Now that's just the cements. I want to also point out the fact that diagenesis also involves the alteration of the minerals that are in the rocks to start with. You're already aware that there are many minerals and that different minerals are stable under different conditions. If you have an arcosic sandstone, something with a lot of feldspar in it, well, yeah, that sandstone was deposited somewhere pretty close to the source, but if you now take that rock and bury it, start subjecting it to pore fluids, the alteration that might have occurred at the surface of the earth while those grains were being transported down the river is now happening underground, but in a contained environment. It's not unusual to see feldspars altering in place. For example, here's a grain where you're looking at feldspar literally being changed into calcite. Calcite is replacing a feldspar grain. A very common situation. Here's another one where you see feldspar being replaced by cerussite. Now I'm focusing in on the feldspars now because frankly the only thing you've had a chance to look at under thin section so far are the siliciclastic components. And of the things you've looked at in thin section, the most unstable of those grains are the feldspars. So look for this type of alteration in the feldspars when you have a chance. But remember, when we finally get to talking about the carbonates are fascinating because minerals change the stability field. It's possible to dissolve out a aragonite to replace it by calcite, then later on replace the calcite by dolomite, then later on replace the dolomite by calcite again, because those minerals are always in a state of almost metastability, as it turns out. Okay, so look for mineral replacement when you're looking down in thin sections as well. Your lab today is diagenesis. I want you to go back to those 2 thin sections I told you to leave space for. Go back and look at the thin sections you were looking at, and to give me some cements on them. Here's what I want you to do. You've done 4 thin sections, 2 immature, 2 mature. I want you to choose 1 thin section from each and tell me everything about the cements. Tell me the type of cement, tell me how the cement formed, as well as ultimately answering the question. I've got the assignment sheet here for you in a second, okay? But this is no new thin sections. What you have to do, and this actually might end up being harder than giving you a new thin section to do, you got to find the thin section you did originally. Not necessarily the same one. It does not have to be the exact same one, but it's got to be the same numbered one. Remember, several thin sections had multiple versions of each, but that might take you a little bit of time to do that, okay? So the thin sections are still there. No new rocks to describe, nothing like that, all right? And this lab will be due on Thursday at 5 o'clock as always.